we got a new start. You guys got your grades starting nice and fresh. You kind of know how the class works. I don't really plan on changing anything. Everything's going to be as is. Didn't have time to update the whiteboards, but you know we're still going to have the same stuff. We're going to have part 2, review, regular homework, etc. So let's do it, guys. Let's begin. So I'm going to give you a quick overview of what Unit 5 is first, because that's our next unit we're looking at. What Unit 5 is basically what derivatives are used for. We've kind of already touched on that a little bit, but today we're going to be looking at how to find minimum and maximum values. We use derivatives for that. We're also going to be looking at a very important theorem called the mean value theorem. It's whenever it reaches an average rate, when your function's rate of change, which is always changing, right? When it actually meets the average rate of change. And the third thing we're going to look at is we're going to see how you can use derivatives to understand the shape of a function. And then finally we'll look at some word problems called optimization problems, where basically you try to find the best possible circumstance that you could get in certain situations. Okay, so that's what derivatives are going to be used for. And after that, we're done with derivatives. We've done everything that we're going to do with derivatives after this unit, because the rest of the year after that is all integral stuff. So this is our last hurrah with derivatives. They'll always be there, but it's our last stuff to learn. So today we're going to identify extrema and critical values by just looking at the graph. Okay, not a lot of calculation will be happening today. It's mostly just concept building. But extrema just means highest and lowest points. So let's take a look at that. I did distribute the notes to you, right? Okay. So what are extrema? Extrema means the extreme values, and there's two types. There's the maxima, which is the highest value, and there's the minima, which is the lowest value on a graph or a function. Okay. Now there's two types. There's you guys see this slide twice on your notes that I gave you. There's what's called the global extrema, also known as the absolute extrema, and then there's another one called the local or relative extrema. So global is kind of easiest to understand. A global extrema is the absolute highest point and lowest point on a function in some specific interval. So like for instance right here, that would be the global max, the highest point. The global minimum would be down here. Actually, I very rarely see anybody using this vocabulary. I usually see this absolute. So that's the absolute max and absolute min. Those are the absolutely highest and lowest points on the graph. Okay. So let's talk about relative extrema. They're also called local extrema. So basically, hills and valleys. Okay. Anywhere where you're at the top of a hill, that's a relative extrema. Or anytime you're at the bottom of a valley, that's a relative extrema. So like this here, that's not the highest point on this graph, right? But it's still the top of the hill, right? So that's a relative max. This is not the lowest point on the graph, but it's still the bottom of a valley. So that's a relative min. So unlike global extrema or absolute extrema, relative extrema can have a bunch, right? Globals have one definite spot that's the highest point and one definite lowest value. The fancy way to word that is just to say it's a y value on the graph that's higher than any point immediately to its left or right. So like here, any point to the left or right of that point, it's going to be higher than any of those immediately to its left or right, so that would be a relative max. For a relative min, a point is a relative min if any point to the left or right of that point is higher than it. Now just so you guys know, it's technically okay to call these relatives as well. So this is a relative max and a relative min. It's still the top and bottom of the hill, right? It just so happens that this is a special relative max and relative min. These also happen to be the absolute maxes and mins, okay? So what's kind of a subtle detail here to point out is that when we're talking about extrema, we're dealing with y values, okay? So if I ask you what's the max, I'm asking you for a y value, okay? In other words, the highest and lowest points. So let's talk about the endpoints of a function. The endpoints of a function, if there are any, can be an absolute extrema, but they're not typically categorized as relative extrema. So for instance, if you had this, you could call this an absolute max because it's the highest point on the curve. But I wouldn't call it a relative extrema. I've actually seen different math books flop on this, though. Some say, no, it is a relative. Some say, no, it's not. I think for our intents purposes, it really doesn't matter. But just to be consistent, I'm going to say that I'm not going to call these relative extremes. I'm just going to call them absolutes. Okay. All right. So here's an example. We want to find all the extrema. All right. So let's start off with absolutes, right? This would be the absolute max or global max. That's the highest point on the graph. This would be the absolute min, lowest point on the graph. But we also want to identify any relative extrema, not just the absolutes. So right here, that would be a relative max, the top of a hill. This would be a relative min. It's the bottom of a valley, if you will. And we would call this a relative max also. Okay? Mm-hmm. The one over there? No, so like endpoints, I don't think we'll ever call them relatives. All right. Am I good to go? All right. So let's do a little guided practice here. We're going to call these, I need to put these on there. They're not on your notes, so you guys might want to add them too. We're going to call those points A, B, and C in all these graphs. Okay, determine if points A, B, and C are extrema, and if so, determine what type they are, relative or global, max or min. And then if not, why not? Okay, so let's see. A, what would you guys say about that? I'm going to say none. Some textbooks will agree with you guys who said relatives. Okay, because it is technically higher than any other point that's around it, correct? But I'm going to say that endpoints are not relative extrema. And it's not an absolute max because that's not the highest point on the graph, and it's not an absolute min because it's not the lowest point on the graph, and it can't be a relative because it's an endpoint. So we're going to say none. Okay. How about B? It is a minimum. I agree with that. What kind of minimum? Good. It could be an absolute or a relative. It's probably better to say absolute, I guess, but it's fine. You can call it relative as well. How about C? It's the highest point on the graph, so we can call that an absolute max. I wouldn't call it a relative max, though, because it's an endpoint. Okay, let's take a look at the next one. Now you'll notice that we have some differences here. I've got open dots, these spots. And over here I've got an open dot here and a closed dot. So for A, what do you guys think of that? I'm going to say none again, yeah. It's like, yep, there's not even a point there anyway, so it's just none. How about B? It's the same as the other one, right? How about C? That's a none. That's none. Now, why is it a none? Well, here's why. Since that's an open dot, there's no point there. Now you might think, okay, we'll just pick the point right below it. That would be the max, right? That's not true, because how many points are below it? There's infinitely many. You might think, okay, well, how about that? There's nothing in between them. Well, if you were to zoom in, you might find some space between those, right? And that'll never stop. You can get infinitely higher. No matter what point you pick below that, there's always going to be one more above it. So technically, this graph does not have an absolute max. There's always something higher. Kind of weird, but that's how it is. So if there's no dot there, it's no good. How about on the next one? A is still going to be none, right? How about B? None again, right? No matter how close you get to this dot, there's always going to be another point closer to that dot, which is going to be lower than the last one you picked. So there's no absolute minimum there. There's no relative minimum. There's nothing. How about C? Okay. So I would just kind of demonstrate what happens if you don't have solid dots. Okay. We're going to be dealing with some theorems probably tomorrow called the extreme value theorem. And basically, it's a theorem that just promises that, yes, this graph somewhere will have an absolute max point and absolute min somewhere. And one of the requirements for you to be able to use that theorem is that it has to be on a closed interval. That means the endpoints have to be solid dots. If they're not, then you can't be sure that there isn't a relative extrema. Okay, so here's what I'd like you guys to do. I want you to find that one. Did I print it for you or no? No? All right, so I'm just going to ask you guys in a minute. You don't have to even write anything down if you don't want to. But I'm going to ask you guys, calling you guys after a couple of minutes, what you guys think about what all these points are, A, B, C, D, E, F, and G. Whether they are, what kind of extrema are they, or if they are extrema at all. Okay? Let's see, a point, yeah, right here at that corner. All right, is anybody not ready? Yes, think. No, so, let's see. What do you think, Orion? How about A? None. Good. Now, just so you guys know, there's something wrong with this sentence, and if you can identify it, let me know. Okay. Well, actually, let me back up. We'll get to that in a second. How about B? What do you think, Gabriel? Good. Relative max. So now, this is where I'll say what I was going to say. What would be wrong with me saying B is a relative max? He's not wrong, but there's something wrong with me saying that. Yeah? Oh, that's a good discussion point, but that's not the issue. But so here's the reason why this is not an absolute max, because there are points higher than. So I'm glad you brought that up. But all right, so it's a subtle detail. I used that word subtle earlier today. No. So technically what we'd say is that, hey, this graph doesn't have an endpoint. Because an endpoint is where the function just stops. So it doesn't stop there. It does keep going, so we can't call it an endpoint. All right, so here it is. B is not a relative max. But let's say that this function was f of x, okay? B is not a relative max, but f of b is. Does that make sense? Because remember, maxes and mins are what kind of values? Y values, and b is an x value. So I'm just trying to point out a little technicality there. But not that you guys had to say that, because I didn't tell you the function's f of x. I'm just trying to use that as a moment to kind of emphasize something. All right. C is tricky. What do you think, Amanda? You would think so, but it's not. All right. Here's why. The technical definition of a relative minimum is that it has to be lower than every point to its left or right. So now if you go to the left, it is lower than any point to the left, but look, if I go to the right, what do you notice about all these points? They're the same height. So that is not actually a relative minimum. Okay? Michael, what do you think about point D? That's right. Huh? Well, it's the same as C in that the answer is none, because it's the points to the left are not higher, right, or lower. All right, how about E? Walter, what do you think? None? Good, because it's an open dot. Zarina, F? Good. Nick? G? It is a relative max. Good job. And then, Matt, what do you think about H? In some textbooks. But I'm going to say none, because we're going to say endpoints can't be relatives. Okay? So there's actually no absolute extrema here. There is no point that is the highest. There is no point that's the lowest, because the points that would be are open dots, and therefore you can always get slightly closer to them and never have an absolute max. There are some absolute or relative maxes, though, but there's no relative min. So there you guys go. Just kind of working out some details there. All right. So let's take a look at guided practice 2. Find the value of the derivative at each relative extrema. What time does this class get out on the flex day? I can't remember. 9:10? 16. Okay. Thank you. All right, so guided practice 2. Find the value of the derivative at each relative extrema. What's the derivative at that point? That relative max there. I'll give you a hint, okay? The derivative is the slope of the tangent line. Okay, so if I drew a tangent line, you know what that is, right? You guys agree it would look like that? What's the slope of that tangent line? Uh-oh. Yeah, it's 0. I'm going to call this f. So f prime of 3, when x equals 3, the derivative is 0. Okay? All right. Over here, let's find another relative extrema. Where's the relative extrema here? At x equals what? 0. So I want to find what's the derivative when x equals 0. What is it? No. Does not exist. The slope from the left and right are not the same, right? Cusps don't have slopes. It's not differentiable. It's coming back, hopefully. All right. Where's my relative extrema on this one? Where are the relative maxes and mins? One and what? Oh, I see what you're saying. Okay, good. Yeah. So I was looking for the x values, but yeah, you're right. So here's my max and here's my min. So I'm going to put the x values for those though, because I'm going to have to, I want to find what's the derivative when x equals those values. So what is the derivative at this point? 0, flat tangent line. How about here? 0, flat tangent line. All right, so let's finish this sentence for me. Whenever you have a relative extrema, the derivative will be 0 or undefined. Okay, so one of our objectives today was, well, tomorrow in particular is going to see how do we use derivatives to find extrema. Well, this is it. If you find your derivative and find where it equals 0 or it's undefined, those are possibly the highest and lowest points on the graph. Relative highest and lowest points. All right. So it's not always that way though. So what we're going to do is instead of calling them extreme, we're going to call them critical values. So a critical value, which we'll call C, is an x value. Notice I underline that. Critical values are x values. A critical value is an x value if the derivative at that point is 0 or if the derivative is undefined. Now you might be thinking, wait a minute, I thought you said that was for relative extrema. Well, sometimes it is. Here's the thing. It's always a critical value, which is sometimes, and usually is, a relative extrema. Okay? Why do we care about critical values? Because if f prime of c equals 0, or if f prime of c is undefined, then that may be where one of the relative extrema are. That may be the highest or lowest point on the graph. But be aware, like I said before, relative extrema are always critical values, but critical values are not always relative extrema. So just because you find a place where the derivative is 0 and a place where the derivative is undefined, it may not be a relative max or a min. You have to test to see if it is, and we'll talk about how to do that later. But there you go. So here's a great example, right? What is the derivative of this function? Okay. Now, what value of x makes this thing equal 0? So that would be a critical value, because that's a value of x that makes the derivative equal 0. That's a critical value. But even though the slope is 0 at this point, this is actually not a relative extrema, because if you guys know what the graph of that looks like, do you guys see how that has a 0 slope at that point? But is that a relative extrema? No. So critical values are where the slope's 0, and usually that gives you a max or min, but there are exceptions, okay? And we'll talk about how you can identify those exceptions later on. All right, so for example 2, identify all critical values and determine if each critical value is a relative, min, or max, or neither. So let's decode this a little bit. Identify all critical values. In other words, we want to find everywhere where the derivative is 0 or undefined. Okay, so let's see here. This point here, I would say, probably like right about here, that's a critical value. That's a critical value because what's the slope at that point? The vertical tangent line, that's undefined. There's no slope at that point. How about at x equals 2? Is that a critical value? Yeah, it is. It's a, yeah, the slope is 0 at that point. I guess I'll write this. How about 3? That's a critical value because what's f prime of 3? It's undefined. It's undefined because it's a cusp. It's a sharp turn. To the left, the slope is 0, but to the right, it's a positive. So, and then I would say that x equals 3.5 is also 1. And that's because if a function's differentiable, that means it's also continuous, right? Which means that if it's not continuous, it can't be differentiable. And this is a hole, so it's undefined. The derivative does not exist there. All right, so no holes, gaps, or jumps, no cusps, no vertical tangent lines. Those are all places where you could have a critical value. All right, now, are any of those are all critical values, so let's circle that and say critical values. Are any of those relative extrema? Like, is 1 a relative min or max, 2, 3, or 3.5? None of them are, right? That's not a highest or lowest point. This one, since it's flat, that's not a relative min. Same thing with 3. And open dots can't be relative extrema either, so we're going to say no relative extrema. So now usually when you have a critical value, usually it is a relative extrema, but I'm using this to show you different situations where it wouldn't be. Okay, so I want you guys to find everywhere where there's a critical value and determine if that critical value gives you a relative min or max or neither. Okay. Remember, a critical value is where the slope is 0 or where the slope is undefined. Okay. So see if you guys can find all the critical values. And critical values are what? X's or Y values. So I want you to give me all the values of x where the function has a slope of 0 or where it's undefined. Those are critical values. And then decide if any of those are relative extrema. Okay? So here we have a slope of 0. Here we have a slope of 0. And here we have a slope of 0. There's no undefined slopes, though. Huh? Oh, good. But the only one that's not a relative extrema would be x equals 0. Hi, it's bathing. Hello? Yeah. So critical values are x equals -2, x equals 0, yes. X equals 2. Relative max. I know. Hi, baby.
Well, but now Mr. Robertson answers. Czar Robertson on the phone. Okay. Yeah.
Chloe, they want you in Miss Lowe's office, so you're gonna. Carol. Yeah, she's supposed to just go to where the counselor's office is. They'll tell you. Where the counselor's office used to be.
I think how they changed it. Why the hell did they change it?
Then I'll just ask.
Bye, Chloe. All right, so there's our answer for that one, guys. So, guys, just a heads up. We never got our textbooks for this class, but I'm giving homework problems out of there. So what I'm doing is I photocopied it, I'll upload it. I don't want to take time to the library to get it. Sorry. We almost never use it, but we might get it soon. We might need it soon. But so I'm going to photocopy it. You're not going to do every problem, obviously, right? So read the Google Classroom post to see which problems you're doing. Okay, and I also photocopied the answer key from the back of the book so you guys can check your odd problems as well.
So,
Huh?
So all like
whole last semester, the usual.
Yeah, nothing new. We're keeping it pretty much the same.